Okay, students. So in this video, we are going to discuss like how to do backward pass. So here we are applying backpropagation algorithm to fine tune our parameters, which are nothing weight from W1 to W8, and we'll do it. We'll do it step by step. So this is how we do it. So if you remember, we have already calculated our total error, right? And that error is containing two terms here. This is EO1 and EO2, which we have already discussed in the previous lecture slide video. So this total error, we want to differentiate it with respect to the parameters W5, W6, and so on. If you remember the structure of our neural network, it was like this, right? So this was error EO1 and this was error EO2, right? And total error is the sum of these. And here we were having weights, right? This was W5, this was W6, W7, and W8, right? And then we had biases B2, B2. So we had biases. So now we'll see like how to differentiate the total error with respect to the parameter W5 first, and then we will generalize it. So we are going to take a derivative with respect to W5, right? So the total error W5. So if I just put it into a computation form, this is how we can see it. That was a net input to the node O out first layer, right? So this was there were two nodes at the output layer. This was the first node O1 of the output, and this was O out O2, right? So this was a net input. This was a net input, and here we are having W5. So first what we do, we take a derivative of a total error with respect to out only, which is here. Then we take a derivative of out with respect to net, right? And then we take a derivative of net with respect to W5. So this is a chain process. You can see in step 1 we are taking a derivative of out with respect to out only. So this is my first step. Then we take a derivative of out with respect to net. This is my second step. And then in the third step, I'm taking a derivative of net with respect to W5. And because this is a chain rule, we then multiply all these three things. And finally, we're going to calculate the derivative of W5 with respect to the total error. Right? Okay, so one by one, first let's say calculate only this term, which is how to calculate the derivative of total error with respect to out one only. As you know that the total error is having two terms. This is my term 1, this is my term 1, and this is my term 2, right? And I'm taking a derivative with respect to out one only. So this second term will act as a constant and it will go away, and I will left with only the first term. When I take a derivative with this first term, you'll see when I take a derivative of this with respect to this first term only, because second behave as a constant, then I will left this part only. Plugging in the value, this is what I will get. Then I calculate my second term. The second term is nothing but we are applying sigmoid to the input, which is net. If we differentiate the sigmoid function, this is the form we're going to get it by plugging the value. This is the second value which in step second, right? Finally, we are calculating the third term, that is the derivative of net with respect to W5. And this is nothing but it's a linear expression, which is a dot product plus bias. If you take a derivative with respect to W5, these two terms will go away, right? Because these are a constant, and this out h1 will left. So finally we get a third term. You need to multiply all these terms 1, 2 and 3, right? Finally you get the derivative of total error with respect to w5. Likewise, yeah, then what you will do, because you are applying a gradient descent, the new w will be what? The new w will be old w, whatever it was, minus eta and the derivative, right? And the derivative we have just calculated it. We plug this derivative into the equation. For now we take some a value of eta, let's say it is 0.5, right? You can take it some other value as well, that's not a problem. And your old w, if you remember in our neural network when we had calculated a forward pass, we used 0.4 uh, 0.4 as a value of w5. So w5 was having 0.4. So you just plug it in this expression to because you are applying gradient descent, and your new w5 will be calculated, which is this one, right? Sorry, I have just used a wrong arrow. So this is the gradient we need to plug it here, right? So finally you get the new value of your w5. Similarly, you get the value of w6, w7 and w8. So here you have seen like how you are calculating the derivative of how you are updating your weights from w5 to w8, which are the weights of a output layer. Now this is fine because the architecture was like this, right? The architecture was like this was my output layer, this was w5, w6, w7 and w8. So you have updated all these parameters here. Now I am left with w1, w2, w3 and w4. So I need to update these four weights as well. So let's see how to do it, right? So the idea is similar to the previous one. What we need to do is to take a derivative of a total to take a derivative with respect to w1 of a total error. We need to apply again a chain rule. So what we will do, we'll just see this node only. So this node is having this net input and this is the output here, right? So what we will do, first we'll take a derivative of a total error with respect to the output h1. So we are taking a derivative with respect to the total error, right? This was my total error, this is my first step. Then I take a derivative of out with respect to net, this is my second step. And finally I will take a derivative of w with respect to net, this is my third step, right? And then I will multiply all these and I will calculate the gradient and I update my w likewise, right? So the as I have said that in first this is my hidden layer, right? First node and second node, and I need to calculate the total derivative of this w1 with respect to the total error, which is here, right? So I take the derivative of out h1, right? I need to take a derivative of this total error with respect to out h1 in my first step. So as you know, my is total error is sum of eo1 and eo2. So because gradient can add it, a gradient is a linear function, we can add it. So I have to add this gradient and this gradient. So I will calculate separately the derivative of eo1 with respect to out h1. Then I will calculate the derivative of eo2 with respect to out h1. And this is my derivative 1 and derivative 2. And then finally I will add these two derivatives to calculate the total error derivative with respect to h1, right? This is why we have written these two terms. So just to recollect or recall, so if you are having multiple nodes at the output and you are calculating some derivative with respect to out here, you need to calculate a derivative with respect to this one. Let's say this is d1, then you calculate derivative with respect to this then this is d2, and you are calculating a derivative here as well, d3. So the total derivative that you are getting is nothing but it's a summation of d1 plus d2 plus d3, right? So this is the same logic we have applied here. So let's calculate the one by one these both terms, right? So first calculate the derivative of EO1 with respect to out H1, right? So let me draw it again so that it look clear to you. So now I am having this EO1 and EO2 as error here, EO1 and EO2. This is my hidden layer first node. So I want to take a derivative of out hidden layer out H1. I want to take a derivative with respect to EO1 first, right? So this is my first term. I will apply the chain rule. What I will do, I will take a derivative of E over with respect to out1, right? I will take a derivative with respect to out1. This is my first step. Then I take a derivative of net with respect of out H1 out O1 with respect to net O1, second step. And then finally I will take a derivative of net O1 with respect to out H1, right? Out H1 with respect to, this is my third step. So one by one I will be going to calculate these three derivatives, right? So this is my these three derivatives I will calculate it, and I will multiply these three derivatives. So I will multiply these three derivatives here. Sorry, this is here, and we calculate the first term, right? This is what where we have calculated the first term. Similarly, we calculated the second term, right? We calculated the second term. Then we add these two terms to calculate the total derivative with respect to out H1, right? Out H1. This is what we have calculated with respect to out H1. So far we have where we have reached here. We have reached uh, so these were the output nodes, right? At output layer we have nodes at hidden layer. So we have calculated the derivative with respect to out O1, right? Out H1, out H1. So we have calculated this term, total error with respect to out H1. In the previous slide we have calculated this. Now we need to calculate this derivative, right? We need to calculate this derivative, which is our second step. It is pretty simple because it's a sigmoid function. You just plug and play, just plug and put the values, and you calculate this. You will have this value. The third is like you calculate the derivative of net H1 with respect to W1, right? Because this net H1 was a linear function. It was Wn1 with I1 plus W2 with I2 plus bias, and you are taking a derivative with respect to W1. So you will left with only I1, right? Because these terms will be constant. You all multiply these all three terms again, and finally what you will get the derivative, you will get the derivative of W1 with respect to total error. And because you are applying a gradient descent, you plug this total derivative here, put some step size, and update your, sorry, this is W1. So you update your weight, and this is what you will get. And similarly you do for W2 W3 and W2 W3 and W4. Sorry, this is W3 W4. Finally, when now you have all your new weights from W1 to W8, if now you just do again this forward pass, right? You do again that forward pass, your weight, the error will go down now. And at first your error was 298, now it is 291, right? This is like a demonstration of like how you can apply a backpropagation algorithm for fine-tuning your neural network. So students, this is all all for feed forward neural networks, where we have discussed forward pass, how to calculate an error, and then we have just discussed backward pass, where we are applying backpropagation algorithm to update the weights. I shall be arranging a discussion class, and I will notify it you on your that Moodle. And if you have any difficulties, we shall be discussing there only. Thank you very much.